Bismillahirrahmanirrahim. Welcome back, everyone. I hope you are all doing well. I welcome you all in class of Elementary Number Theory by David M. Burton. Lastly, we have covered up to question number 18. In today's lecture, we will start from question number 19. We will just solve question number 19 in this single lecture because this question has 5 parts. So question is something lengthy. Question number 19, establish each of the assertion below. If a is any arbitrary integer, you have to show 6 divides this product a into a square plus 11. This is a very simple part. You can solve this question by mathematical induction. Still, if you face any problem, you can comments me. Inshallah, I will solve this problem. In B parts, it is stated as if a is any odd integer, then show that 24 divides a into a square minus 1. I will use the same strategy here that I have used in question number 18. Firstly, we convert 24 as the product of two numbers which are relatively prime. So I can break 24 as 3 into 8 with GCD of 3 into with GCD of 3 and 8 is 1. Mean to say 3 and 8 are relatively prime. Actually, I will use the corollary number 2 of theorem 2.4. That corollary says if some number a divides c and b also divides c with GCD of a and b is equal to 1. This corollary says in this case the product AB must divide C also. So I have to show 24 divide this product. So firstly I will show this product is divisible by 3, then it is divisible by 8. Finally, by using this corollary I will say this number a into a square minus 1 is divisible by 24. So we can write a into a square minus 1 as a minus 1 into a plus 1. As it is given that a is an odd integer. So if a is an odd integer, we can write it as a is equal to 2k plus 1. You know, this is the form of an odd integer. So replace a is equal to 2k plus 1 here. This become 2k plus 1 minus 1. This is 2k. When you put a is equal to 2k plus 1, this become 2k plus 1. And when you put here a is equal to 2k plus 1, this become 2k plus 2. Secondly, taking common 2 from this bracket and multiply that 2 with here, this becomes 4k into k plus 1 into 2k plus 1. The factor 2k plus 2 becomes 2 into k plus 1. This is my k plus 1 and this 2 is multiplied by 2k. Now you can notice that for any integer k into k plus 1, these are always two consecutive integer. And we know the product of two consecutive integer is always even number. For example, if 3 and 4, these are the two consecutive integer, their product is 12. This is an even integer. If you take 4 into 5, these are also consecutive, their product is 20. This is also an even. So whenever you will multiply any two consecutive integer, their product is always an even integer. So we can write k into k plus 1 is equal to 2m. So substitute k into k plus 1 with 2m. This become 4 into 2m into 2k plus 1. Now 4 into 2, this becomes 8m into 2k plus 1. So this shows that this number is divisible by 8 because this is the multiple of 8 here. So this implies 8 divides a into a square minus 1. So this our first task is complete, has been completed here. It is also obvious. Next we have to show that 3 divides a into a square minus 1. As a into a square minus 1 can be written as a minus 1 into a plus 1. I have written, it is also obvious that a product of any three consecutive integer. You can notice that these are the product of three consecutive integers. The product of three consecutive integer is always divisible by 3. If you take any three consecutive integer like 3, 4, 5, one of them is always divisible by 3. Suppose you take 4, 5, 6, then 6 is divisible by 3. So whenever you will take any three consecutive integer, one of the integer is always divisible by 3. So it is obvious that 3 divides a into a square minus 1. So both of the target has been completed here. 3 divides a into a square minus 1, 8 divide 8 into a square minus 1 by using corollary 2 of theorem 2.4 that I have discussed. Product of 3 into 8, that is 24, divides a into a square minus 1. So this completes our B part. In the C part, we have to show if a and b are odd integer, then 8 divides a square minus b square. It is given that a and b are odd integer. So we will take the form of odd integer here. A is equal to 2k plus 1 and b is equal to 2m plus 1, where m and k are integers. So now substitute these values of a and b in a square minus b square. So whenever you put here a is equal to 2k plus 1, this becomes 2k plus 1 whole square, and this becomes 2m plus 1 whole square. Now expanding the square, this gives 4k square plus 1 plus 4k, and this becomes 4m square plus 1 plus 4m. Taking 4k common from these two terms, this become 4k into k plus 1. Similarly, whenever you take 4m common from these two terms, this becomes 4m plus m plus 1, and this one and this minus 1 after opening this bracket becomes cancel. Now again, as we have discussed above in above question, k into k plus 1, these are the product of two consecutive integers. This is k and this is k plus 1. So these are the consecutive integers, and this is the product of two consecutive integer. Product of two consecutive integer always an even integer. So we can write it as 2 into k dash, where k dash is some integer. Similarly, we can replace m into m plus 1 as 2m dash, where m dash is some integer. Now, this becomes 8k dash minus 8m dash, taking common 8. So this number is clearly divisible by 8 because it is a multiple of 8. This shows that 8 divides a square minus b square, because your left side is a square minus b square. This shows 8 divides a square minus b square. That completes the problem. 19D bar. This is a interesting problem. If a is an integer not divisible by 2 or 3, there is some integer a which is not divisible by 2 or 3, like a could be 5, because 2 does not divide 5, and 3 also does not divide 5. Then we have to show that 24 divide a square plus 23. Okay, like you can understand this problem by this counter example. If you put a is equal to 5 here, this become 25 plus 23. Answer is 48. Clearly 48 divisible by 24. I will share the solution of this problem by using two methods. Firstly, I will use the corollary 2 of theorem 2.4. I will split 24 as a product of two number 3 and 8, where 3 and 8 both are relatively prime because their GCD is 3 and 8 is 1. Firstly, we will show that this number a square plus 23 is divisible by 3. Secondly, we will show that this number is also divisible by 8. Lastly, we will use the corollary of theorem 2.4. So let's show that 3 divides a square plus 23. 3 divides a square plus 23. It is given that a is not divisible by 3. That is 3 does not divide a. It means a is not a multiple of 3. Clearly, when a number is not divisible by 3, it means when a number is not divisible by 3, it means that number is not a multiple of 3. So this shows that a cannot be of the form a is equal to 3k. So a must has the following form. If a has not this form, then it means that a has the form 3k plus 1 or 3k plus 2. Suppose you think why a has not this form 3k plus 3. If you write this as 3k plus 3, this becomes again a multiple of 3 here by taking 3 as a common. So there are the only two possibilities for two possible form of a. Either it will be 3k plus 1 or it will be 3k plus 2. So when a is 3k plus 1, so we substitute a is equal to 3k plus 1 here, a square plus 23. So this becomes 3k plus 1 whole square plus 23. By expanding square, this becomes 9k square plus 1 plus 6k plus 23. 1 plus 23, this becomes 24. Taking 3 as a common, this becomes 3k square plus 2k plus 8. Clearly, this number is a multiple of 3 here. Clearly, this is a divisible by 3. So this shows that 3 divides a square plus 23. So in this case, this number is divisible by 3. Now if a has 3k plus 2 form, again substituting a is equal to 3k plus 2 here, this becomes 3k plus 2 whole square plus 23. By expanding square, this becomes 9k square plus 4 plus 12k plus 23. 4 plus 23, this becomes 27, and after taking 3 as a common, we have 3k square plus 4k plus 9. Again, this number is a multiple of 3. This shows that 3 again divide a square plus 23. So in both cases, 3 divide a square plus 23 here. Next, we show that 8 divides a square plus 23. It is given that a is not divisible by 2 here. If a number is not divisible by 2, it means that number cannot be an even integer. This shows that a is not an even integer. So if a is not an even integer, then there is only one possibility for a. It must be an odd number. In integers, there are only two type of numbers. Either they are even or they are odd. So when you say the number is integer is not even, so there is only one possibility, it is an odd integer. So if a is an odd integer, then an odd integer has the form 2k plus 1. So a can be written as a is equal to 2k plus 1. So substitute a is equal to 2k plus 1 here. This becomes 2k plus 1 whole square plus 23. So after expanding the square, we have 4k square plus 1 plus 4k plus 23. 1 plus 23, this is 24. Taking 4 as a common, we have k square plus k plus 6. Taking k common from these two terms, this becomes k into k plus 1 plus 6. Again, since k and k plus 1 are the consecutive integers and their product k into k plus 1 is an even integer. So I can write k into k plus 1 is equal to 2m. So replace k into k plus 1 with 2m plus 6. Taking 2 common from these two terms, this becomes 4 to the 8 plus m plus 3. Clearly this number is divisible by 8 because this is a multiple of 8. This shows that 8 divides a square plus 23. As 3 divides a square plus 23 and this number is also divisible by 8 with GCD of 3 and 8 is 1. This shows that their product 3 into 8 24 divide a square plus 23. Alternatively, you can do this question as it is given that 2 does not divide a. It means a is not an even integer. It means a is not a multiple of 2, that is a has a not form of 2k. Similarly, 3 does not divide a. it means a is not equal to 3m, that is a is not multiple of 3. So let a has the possible form other than this. A has a possible form 6q plus r. A is equal to 6q plus r form. This form can be done as by division algorithm. When you divide a by 6, there will be some quotient q. This becomes 6q, and after subtracting 6q from a, we have some remainder r, and this remainder r either is 0, 1, 2, 3, 4, 5, 6, 4, 5. Now we check the different possibility for this remainder r. If your remainder r is 0, so when you put r is equal to 0 here, this becomes a is equal to 6q. But this is not possible because a cannot be a multiple of 2 or 3. Because, in other words, you can see here this number 6q. 6q is divisible by 2, and 6q is also divisible by 3. Both number 2 and 3 divide 6q. But it is given that a is not divisible by 2 or 3. So this is not possible that your r is 0, because in this case a becomes a multiple of 6 here. So ignore this case. In the second case, if r is 1, then your a has a 6q plus 1. This number is not divisible by 2 or neither divisible by 2 nor 3. So this is possible case. If r is equal to 2, if your remainder is 2, then a becomes 6q plus 2. Taking 2 as a common, we have 2 into 3q plus 1. But this is a multiple of 2, so this complete number is an even integer because it is a multiple of 2 here. So this case is also not hold, because your number should not be multiple of 2. If r is equal to 3, your remainder is 3, then now a becomes 6q plus 3. Taking 3 common, this becomes 3 into 2q plus 1. This shows that this number is multiple of 3 here. But this is not possible because it is given that a is not a multiple of 3. So this case is also not possible. If r is equal to 4, this becomes 6q plus 4. By taking 2 common, this has a is equal to 2 into 3q plus 2. This is again an even integer because it is a multiple of 2. So this is not possible. When r is equal to 5, this becomes a is equal to 6q plus 5. This is possible. So only possibilities for a are either it is 6q plus 1 form or it is 6q plus 5. Now we will show that for this values of a, these possibilities for a, we will show that this number a square plus 23 is divisible by 24. So when you put a is equal to 6q plus 1 here, this becomes 6q plus 1 whole square plus 23. Taking expanding square, this becomes 36q square plus 1 plus 12q plus 23. 1 plus 23, this becomes 24. Taking 12 as a common, this becomes 12 into 3q square plus q plus 2. This becomes q into 3q plus 1 plus 2. For any integer q, although these two numbers are not consecutive integer, but for any q, any integer q, this number q into 3q plus 1 is always an even integer. How this is possible? You know, if q is an integer, then it will be either even or it will be either odd. If q is even, then 3 times q is also even integer, because when you multiply an even integer with any number 3 or 4 any number, this will be an even integer. So 3q is an even integer. 3q plus 1, this become even plus 1. Even plus 1 means even plus 1 is odd. This become odd. Finally, when you multiply this complete number 3q plus 1 with the q, where your q is an even integer, even into 3q plus 1 is an odd integer. So even into odd, this is again an even integer. Similarly, you can verify that if q is odd, then again this number q into 3q plus 1 is an even integer. So in both of the cases, this number is always an even integer. So I can write this number equal to 2m, where m is some integer. So replace this complete number with equal to 2m. So So this become 2m plus 2. Taking 2 common, this become 24 into m plus 1. And finally, you can say that this number is divisible by 24. Similarly, when a is equal to 6q plus 5, then again you can verify that this number is divisible by 24. Last part, E part. This is also important. If a is an arbitrary integer, then you have to show 360 divides the product, this product, and this product has a 6 consecutive integers. Product of this is a product of 6 consecutive integers. So to prove this, firstly I will make the prime factorization of 360. The prime factorization of 360 is 2 raised to the power 3 plus 3 into 3 raised to 3 square into 5. That is 8 into 9 into 5. Again, you can notice that the GCD of these three numbers is 5 because there is only one common factor in all of these, that is 1 here. So that GCD is 1. Otherwise, you can find GCD by a prime factorization or by using a long division method. So they are relatively prime. Let the given product is denoted by m. This is my given product, and I am writing this is equal to m. So let this is my product m, and say this is star. Now I have to show that 360 divide m. If each prime factor of 360 separately divides m, we need to show that 8 divides m, 9 divides m, 5 divides m. In order to show that 360 divide m, I will show that each of the factor 8, 9, 5 separately divide 360. Actually, this is not different from the corollary. We have a general result. If a1, a2 up to so on an, these are the some n integers, then all ai divides m if and only if their LCM divide m. So to show that 360, that is the LCM of 8, 9 and 5. 8, 5 the 40, 49 the 360, yes. 360 is the LCM of these numbers. So if these number separately divides m, then their LCM, that is 360, also divide m. So our target is shown that each of the number divide m. So divisibility by 8. In problem number 18, we have shown that 24 divide the product of any 4 consecutive integers. In our given problem, we have a 6 consecutive integer, 1, 2, 3, 4, 5, 6. But in problem number 18, we have shown that if any 4 consecutive integer is divisible by 24, product of any 4 consecutive integer is divisible by 24. Suppose these are the 4 consecutive integer which are divisible by 24. So it means these numbers are multiple of 24. 24 multiples of 24, like 24k. Now we have the remaining 2 integer, this a plus 2 into a. Clearly this whole product is divisible by 24 because this is multiple of 24. So when you say in the product of 6 consecutive integer, any 2, 3 or 4 consecutive integers are divisible by 24, it means the complete product is divisible by 24. Now 24 divide m. M is the product of what is m? M is this product of 6 consecutive integer. As 24 divide m, as 8 divide 24 and 24 divide m, this implies 8 divide m. This is the transitive property of divisibility. Transitive property of divisibility says that if a divide b and b divide c, this implies a divide c. So 8 divide 24, 24 divide m, this implies 8 divide m. So this is our first target. Next we show that the number is divisible by 5. In problem number 18, we have also shown that 120 divide the product of any 5 consecutive integer, that is 120 divide m. As 5 divide 120 and 120 divide m, again by using the transitive property of divisibility, 5 divide m. Lastly, we showed that the number is divisible by 9. In problem number 18, we have also shown that the product of any three consecutive integers is divisible by 6. Suppose the first three consecutive integers is divisible by 6. From that product, from this product, this is the product of 6 consecutive integer. We say the product of these three consecutive integer is divisible by 6. So 6 divide the product of these three consecutive integer. As 3 divides 6 and 6 divide this product, this implies 3 divides product of these three consecutive integer. And it is also clear that we have shown above that the product of any three consecutive integer is always divisible by 3. Similarly, the product of next three consecutive integer a into a plus 1 a plus 2 in star is also divisible by 3. It means the whole product m is multiple of 9. This shows that 9 divides the m. Hence, finally, 8 into 9 into 5 divides m. That is 360 divided m. So, I hope now you have a clear understanding of question number 19. This is very interesting and very nice question. Inshallah, in the next lecture, we will start from question number 20. If you find this lecture is helpful, kindly like, share, and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.